The Session 3 lecture is a continuation of linear algebra. We are going to start with the discussion of linear inequalities just in general, and then use that to kind of delve into linear programming, pivots, simplex tableaus, and use that to solve maximization and minimization problems. And I know that's a lot of words, but I will explain them in turn and make them not quite as abstract for you. So the problem of the week this week, we're back in the widget business again, which I guess makes 2 weeks in a row of widgets, or at least 2 of the last 3 weeks. So we're manufacturing 2 types of widgets, and I tried to kind of ape a real-world situation here in the sense that almost any kind of problem in the real world is going to have constraints, whether they be monetary, physical, or otherwise. So we have a problem where we have a certain number of hours to make a widget, but we also have a limited number of hours available and different profits depending on what kind of widgets we make. So I wanted to make the problems more and more realistic as the weeks rolled on here. So keep this problem in the back of your head or the front, and let's start talking a little bit about inequalities. Okay, so I'm going to review, and this is going back to what I would call regular algebra as opposed to linear algebra. Okay, so when we look at inequalities, the first thing we need to think about is it inclusive or not? This goes back to either less than, greater than, or less than or equal to, greater than or equal to. So if we have a condition of equality, that gives us a solid line. If we do not have a condition of equality, that gives us a dotted line. Okay, so let's look, make this a little less abstract. So if we wanted to graph the inequality 4x plus 2y is greater than or equal to 8, okay, the first step to doing that is to treat it as an equality. Okay, and then using the methods that we discussed in week 1, solve it for y and go ahead and graph it. Okay, so that's kind of the first step. The next step, because it contains equality, you want to have a solid line, and then we want to figure out, is our solution region, okay, the place where 4x plus 2y is indeed greater than or equal to 8, is that going to be to the right or to the left of our line? Okay, and the best way to do this is take a test point, the easier the better, and see if it fits. If it fits into the equation and makes the equation true, then that's the region that you shade in. If it does not make the equation true, then you shade in the other region. Okay? Kind of an oversimplification, but that is the way to solve inequalities. Okay, so that was a single equation. What about 2 equations? And eventually more than that. Okay, so if we're asked to find the points that satisfy both inequalities, x plus y is greater than or equal to 4, and y is greater than or equal to x plus 3, okay, the first step we need to do is we need to graph both equations. Okay, you can see which one's red and which one's blue. And now, as you can see on the graph, we have 4 different regions where this could be true. Okay, basically it could be true to the left, to the right, to the top, or to the bottom. And now we have to figure out where are both of these equations satisfied. Okay, and here I put them as A, B, C, and D. Okay, so now instead of trying 2 test points, we're going to try 4 test points. And we're going to see which region both of the equations is valid for. Okay, so here are the 4 test points that I chose. And as you can see, the only place where these are valid would be region A. Okay, so in this case, the solution would look like this graphically, okay, with that upside down triangle on top shaded in. That would be your solution region. Okay, one more example, okay, all ordered pairs, so the entire solution region that satisfies these 2 equations, y is greater than 3 minus x, and y is less than 2 minus x. Okay, so this is what the two lines would look like graphically, and now we have three regions, below, above, and between, to look at. Okay, and as you can see, sorry, I got excited and skipped ahead there. As you can see, it is not valid in any of the three regions. Okay, so what does that tell us? Okay, inconsistent equations. Okay, the solution set for y is greater than 3 minus x is in blue. The solution set for y is less than 2 minus x is in red. Okay, and there's no point where they intersect. Okay, so this is what inconsistent equations look like when you're trying to tie them in with inequalities. Okay, so foundationally, this is kind of how inequalities work. Now, what happens when you go, instead of one or two variables and one or two equations, what happens when you get a whole mess of variables, kind of a more real-world problem? Okay, and as a good example of a real-world problem, we have our widget factory. Okay, so how do we set this up? How do we incorporate all of the information given here into a single doable problem? Okay? What we're looking to do essentially is we want to maximize the profit. Okay? So we know we make $130 for the number for each basic widget, and we know we make $160 for each advanced widget. Okay? So we want to maximize the profit. Okay? And this is, again, something you're probably looking to do in almost all of your jobs. You're looking to maximize or minimize something under certain constraints. Okay? And these constraints are, okay, the number of basic widgets and then twice the number of advanced widgets, okay, has to be less than 80. Okay, again, because this is a limitation. If you look back at the prior page, this is the number of labor hours. Okay, so you only have 80 hours available in fabrication and 180 hours available in finishing. So that is where these two equations come from. x1 plus 2x2 is less than equal to 80. 3x1 plus 4x2 is less than equal to 180. Okay, so make sure you understand how that connected to this. I hope I'm not making you dizzy by going back and forth here. Okay, so understand how you got from this setup to these three equations for the profit and for the limitations on the number of hours. Okay, and this is what is called a linear programming problem. Okay, you're trying to maximize a certain function under certain constraints. That's basically what a linear programming problem is. Okay, and granted, this is a relatively simple one, but as you'll see, even a problem with this few variables is not that easy to solve. Okay, so what we want to do is we want to convert this into more or less of a matrix problem, and then we can use the methods that we learned last week to manipulate it into a way where we can kind of make some sense out of it. Okay, so what we want to use are called slack variables, because we're going to have more equations to match the number of unknowns that we have, or more unknowns to match the number of equations we have. Okay, so we're turning the linear programming problem into a system of linear equations. Okay, so the slack variables are just extra variables that we're putting into the equation to kind of make up for information that we don't necessarily have yet in the problem. Okay, so now we have something that looks a little bit more familiar. Okay, we have three equations. It looks like we have three unknowns, but we actually have 5 unknowns. But this is, it looks a lot like a 3 by 3 matrix or a 3 by 4 augmented matrix, which is something that we know how to solve. Okay, and what we're going to do is we're going to make things a little more confusing in order to make them right as far as setting it up as a matrix. Okay, we want to have every single variable present in every single equation. Okay, so we have all 5 variables present, and in some cases they're kind of dummy variables because they have zeros in front of them, but this is just for the sake of setting it up as a matrix. Okay, and because, as we mentioned earlier and in prior lectures, we have more unknowns than equations. Right now we have a dependent set of equations. Okay, there is no unique solution to this. But we're going to learn how to find some solutions. Okay, the variables that we added into the equation, not our x's, our s, s1, s2, and p, okay, these are called basic variables. Okay, why are they called basic variables? If you look back to this page, the only thing they have in front of them is either a 0 or a 1. They have nothing else in front of them. Okay, and this will be the case anytime we set up one of these types of equations. Okay, you have basic variables, and probably not so surprisingly, the x1 and x2 are the non-basic variables. Okay, so the first thing we're going to do is the simplest solution, kind of almost the dummy solution. Okay, you set the non-basic variables equal to 0. Okay, so this is what happens if we manufacture 0 of either type of widget. Okay, this is what our equation looks like. And it's called, okay, whenever you have the non-basic variables equal to 0, it's called the basic feasible solution, okay, which we'll get more into later. Okay, but as you can see, the solution to this will be S1 equals 80, S2 equals 180, and the profit, of course, is going to equal 0. Okay, so going back to our original equation, okay, with all those variables in there, this is what it looks like, okay, where I put the x1, x2, s1, s2, and p on top of the columns so you can kind of be aware of which variables they represent. So we have the first equation, which is x1 plus 2x2 plus s1 equals 80, and the second equation, which is 3x1 plus 4x2 plus s2 equals 180. Okay, and where does that bottom come from? If you go back to that original equation there at the bottom, okay, that's where that last equation came from. The negative 130x1 minus 160x2 plus p equals 0. Okay, that was the profit equation. Okay, that's the one on the bottom there. Okay, notice that's the only equation that has anything in the p column. Okay, and when you have it set up like this with all of your variables in one place, and the quantity you want to maximize or minimize is at the very bottom, this is called the initial simplex tableau. Okay, and this is something that you'll see pretty often because, as I mentioned, almost any real-world problem will have something that you want to maximize or minimize. Okay, and the reason why I did all the stuff with graphing, okay, this is what the equations would look like. Okay, fabrication in red, finishing in blue. Okay, so the only place where they're actually both true is in the green section. Okay, and again, have patience with me. This will make sense later. Okay, and those points, as you can see, it's where they intersect the axes and where they intersect each other. Okay, so going back to our initial simplex tableau, okay, the first thing you want to do in this process is you want to find the most negative value in the entire matrix. Okay, in this case, the most negative value is negative 160. Okay, and this value locates the pivot column. Okay, once we have the pivot column, what do? We can divide the values on the right-hand side by the numbers in that column. Okay, so you divide the first row by 2, the second row by 4, and once you divide out, whatever the smallest number on the right is, okay, in this case the smallest number on the right is 40, that will tell you where the pivot row is. Okay, and the intersection, as you can see, of the pivot row and pivot column tells you where the pivot is. Okay, and I know this is all seeming tricky, and let me again give you a disclaimer here. This is something that you will do using Python or another type of computer program where it will do it for you, but I just want you to understand kind of what happens behind the scenes. So if this is getting way out there, please don't worry too much. This is nothing that I would ask you to do manually. It's just something I want you to understand how it all comes about. Okay, so do keep that in mind. Okay, so the next thing we want to do is we want to pivot. Okay, we know what the pivot was. It's where the pivot column and pivot row intersect. Okay, so we want to divide by 2. Okay, we want to turn it into a 1, which in this case we do by dividing the whole row by 2. So you turn the pivot into 1. Okay, and that is our row. It's now 1/2, 1, 1/2, and 40. Okay, and here is a little bit of matrix magic going on here. Okay, and what we're trying to do basically is we're trying to get zeros in the pivot column. Okay, other than the pivot itself, we're trying to turn everything else into a 0, which you guys know how to do from last week using matrix manipulation. Okay, and now the bottom tableau, okay, which we see here. It's our new tableau, and we need its basic feasible solution. Okay, so the non-basic variables here are x1 and s1. Okay, and why are they the non-basic variables? Because they have something besides 1s and 0s there. Okay, so we set these guys equal to 0 in order to find the new basic feasible solution, and this will give us the results that x2 equals 40, s2 equals 20, and profit equals 6,400. So if you go back to the graph, which is right here, okay, what that tells us is that along the y-axis at the point 040, the profit will be $6,400. So if you look at that point, sorry, I can't actually point on here, but if you look at the point 040, that represents $6,400 profit. Okay, and we're going to keep doing the pivoting until we're out of stuff to pivot on. Okay, so the lowest value in our third row, in our new third row, is -50. So that's our pivot column. So we do the same thing again. This time, okay, we're going to pivot where the row with the 20 and the row with the -50 intersect. So the pivot is going to be 1. Okay, we do the same matrix manipulation again to get zeros everywhere else in that column except for where the pivot is. Okay, and this time the non-basic variables are going to be S1 and S2. Okay, so if we set these guys equal to 0, we get x1 equals 20, x2 equals 30, and the profit, which you see on the bottom right, is going to be $7,400. Okay, so this is the point on the graph, which I'm not going to go back to because I know that's kind of getting kind of confusing. But if we make 20 of the first kind of widget and 30 of the second kind of widget, we'll have a profit of $7,400. Okay, as long as we have a negative value in the last row, we need to keep pivoting. Okay, so the final pivot, we hope the final pivot, is along -20. So we divide everything by 3/2, and as you can see here, sorry, you get a negative value when you divide the -2 by 20. Okay, that gives you a negative value. Sorry, the 20 by -2, that should say. So you cannot have a pivot when you have a negative value in the right-hand column. Okay, so what that tells us is that the pivot itself is going to be 3/2. Okay, you can't pivot on a negative is basically what it comes down to. Okay, so we're pivoting on 3/2, we're not pivoting on -2. Okay, same approach. To turn that 3/2 into a 1, we need to convert the -2 and the -20. We need everything else to be converted into zeros. Okay, playing around a little bit with our matrix manipulation. Okay, this time, sorry, as you can see, x2 and s2 are the non-basic variables. Okay, they're the non-zeros. So setting these guys equal to 0, we find our basic feasible solution. For this case, that is x1 equals 60, s1 equals 20, and the profit is $7,800. Okay? There are no more negative values in the bottom row. Okay, as you can see here. No more negatives in the bottom row. Okay, so that means we're done. So we have 4 possibilities. Okay, and we kind of cheated by showing you those on the original graph. Okay, if we make 0 widgets, we have a profit of 0, 0 basic, and 40 advanced. The profit is 6,400. Okay, and skipping to the best part, if we make 60 basic and 0 advanced, the profit is 7,800. Okay, so our best solution, okay, and I'm going to go back one more time. This is it, I promise, to the graph. Okay, our best solution is the point 60, 0. Okay, making 60 of the first type of widget, 0 of the second type of widget. Okay, when you consider everything involved, that gives you the most profitable situation. Okay, so only basic widgets. And I realize that is a confusing process to go through manually. Just understand the process in a basic way, and then you let the computer program do the work for you. But basically, realistically, as I said, you're going to have problems where you want to maximize or minimize something quite a bit of time, and they're often going to be constrained by either physical or economic conditions. So this is a kind of a good example of a realistic type of problem. It's something we will also tackle later using different methods, but you learned the hard stuff. So you understand this on a basic level, which is an important thing to do before we kind of go on to the next topic.